code. All right, so indirect treatment meta-analysis is basically we want to compare an intervention with one comparator, with more than one comparator. So in all the previous sections that we've been looking at, we're comparing treatment and placebo, or treatment one versus standard of care. That's what we've been doing, or one population intervention versus nothing. But there are some scenarios, and this is often the case in drugs and pharmacoepidemiology, where you're interested in understanding whether drug A is better than drug B and drug C, and typically there will have been maybe a number of studies that have been conducted by different researchers, different companies, and each of them has compared to something. So let's take hypertension, for instance. Maybe one study has compared amiloride with placebo. Another study has compared, maybe what's another antihypertensive? Maybe one calcium channel blocker with placebo. Another study has compared maybe another diuretic.
Diuretics?
Yeah, with placebo. Or they might have compared a diuretic with a calcium channel blocker, or a beta blocker. So you have different groups, but you're trying to understand. The research question might be that among individuals who have renal pathology, right, is there one particular antihypertensive that's better? If you're looking at efficacy, or you might be interested in maybe, is there any antihypertensive that is more likely to worsen the risk of renal pathology in these people? Maybe it was more likely to cause them to progress faster, right? So you might be looking at safety, you might be looking at efficacy, whatever you're looking at, the same outcome, but you have multiple interventions that you're trying to compare. In that scenario, you use indirect treatment meta-analysis, which is also known as network meta-analysis, right? And you'll see why it's network meta-analysis in a moment. But this is the library that we use here is net meta. It's not the same ones that we've used above, where we're using meta4 or meta. So this is net meta. So if you run this so that you can bring up the library, and the structure is very similar, just that there are a few differences in this case. Now, the question that we're looking at in this case is, if you go back to the media campaigns story that we've been talking about since the beginning of the class, a media campaign can be many things. It might be a TV campaign, it might be a radio campaign, and it might be maybe social media, it might be a mix, right? And someone is saying, does it matter which type of media campaign you're looking at? You can answer this question using heterogeneity in the previous analysis, where you assume a media campaign is a media campaign regardless. Or you can answer this question using network meta-analysis, where you say one media campaign, where you say radio is different from TV, and you examine the outcomes depending on whether it's radio or TV. It's essentially the same thing, where you can assume antihypertensives are the same, or maybe the different groups of antihypertensives, or different specific antihypertensive, and you can look at each one differently. Okay, so this is the code that is used. You have to use the summary estimate that you've already generated. In this case, we're looking at continuous outcome of intake of fruits and vegetables. So, and this is the main difference. So TE stands for treatment effect. Standard error of TE is just a standard error, and this is standard error of the treatment effect, which is standard error of the mean difference. But you have to specify what you're comparing, right? So what's the first treatment, what's the second treatment? If there's more than one, you specify which treatment is treat 3, treat 4, and like that. And in this case, we're comparing two interventions with, we're comparing two interventions. All the studies that we have two interventions. This variable media, and let me show it to you. I think it should be here. Sorry that I'm moving so fast. This is this variable media, right? In one study, the first study was a TV study. They compared a TV campaign to nothing. In another study, they compared a radio campaign to nothing. In another one, they compared a mix of radio and TV to TV alone, right? Or this one, they looked at TV and radio. Okay, so this is just a convenience thing that we're using for the purpose of teaching this class, right? Ideally, you wouldn't include some of these in this if your interest was in media campaigns. But if your interest is in looking at the effect of the specific media, then you would be able to look at studies where they compare TV versus radio, TV versus nothing, or all of these versus nothing. So this is how you would label the variable. Okay, so you have media and comparator. This is the first treatment. This is the second treatment. Okay, and if you go back to the code, so we have treat 1 here called media, treat 2 here called comparator. All right, and so basically the study label, the data, and in this case, the summary measure is mean difference. You remember here we have TV, radio, mix, and nothing. Those are the 4 different interventions that we're comparing in this network meta-analysis. But we're going to choose nothing as the comparator. So we specify here as the reference, right? So essentially, we'll be able to compare everything to nothing, but also everything to each other. So now you create this meta-analysis object and you click run. Okay. So once you click run, now you can generate the summary. So if you look at, this is the summary that we had. They compared TV to nothing, radio to nothing, like that. Okay. And these are the effects in the individual studies. This basically the estimates from each study. And this tells us how many treatment arms each study has. Now, this is the model that we're interested in. Okay. This is leverage, but this is the, so you have to keep scrolling down. This is the common effects model. This is the outcome that we are really interested in for fixed effects. Okay, so now the analysis then just looks at everything and says, for all the studies where they had a mix, this is the full defect estimate compared to if they had nothing. This looks at the study for all the studies where they had used radio compared to nothing. All studies where they used TV compared to nothing. And what you then see, remember that the effect, this effect of interest is mean difference, so that the null is 0. The null is 0. So that means that the confidence intervals in this case do not cross 0. And so they're statistically significant. Okay? Their p-values are less than 0.05. But what we can then see is that when you use a mix of radio and TV, you have a greater effect than if you use radio alone or TV alone. That's how you would think about it. And that's what you find in the fixed common effects model, which is a fixed effect. And we have fairly similar findings using the random effects model. Numbers are different, but the pattern is the same. Okay. And we can look at the I-squared, it's 7%. But we can visualize these results. We can visualize these results using the network graph. But before we go to the network graph, does everybody understand everything I've said from beginning here now to this point before we make it complicated further? Is it clear?
Yes, sir.
Okay. Anyone else?
Yes, it's
Okay, thank you. So the network graph will help us to visualize the effects. So here, we then run this code. This code is basically this first statement is to just specify what we are going to see, and then and this is to reorder it. So one is nothing, two is mix, radio, TV in that order, and then we create the graph, and this is what the graph looks like. So we're essentially looking at the studies that we're looking at have compared TV against nothing, make the mix against nothing, radio against the mix. We don't have any studies comparing radio against nothing. I feel like this might be wrongly labeled because I think we had radio against nothing. Yeah, we did have radio against nothing. So this might be wrongly labeled. But if you correctly label this, then you will get a graph that looks like this, where you have studies that have you have studies of this one against that one, that against that, that against this, in that order, and you can then rank the studies, okay? And you can then rank the studies that then from the smallest values to the largest value, or from the largest values to the smallest values. And here it says small values are bad. Bad in the sense that are not the best. The best are those with the largest values. And we've seen that earlier too, when we've seen here essentially that the mix is the best, followed by radio, followed by TV. And if you rank it, you'll find the exact same thing. The mix is the best, followed by radio, followed by TV. And the P-score basically is just a proportion, that just helps you to rank what proportion, what percent, what's the likelihood of your results being true. Okay. And then you can do a forest plot. But this forest plot is different from the forest plots we have seen, where the forest plot are by study. This is a summary forest plot by intervention, right? So for TV compared to nothing, this is the effects. For radio compared to nothing, for the mix compared to nothing, this is what you get. And you can, you can include this forest plot in your studies as well. And then we have the publication bias. Okay. Same thing, publication bias using funnel plots. Okay. And in this case, it gives you it tells you each study basically. But first of all, you should look at symmetry, and you can see that there are more studies on the left compared to studies on the right. So that tells us there might be some publication bias going on. So you might be able to use trim and fill. I think we can explore that. But basically, this is what the forest plot would look like. It indicates each study what interventions were being compared, right? And so you might even be able to look at each and say, maybe it's the studies of TV where there's a missing study here on the right. And you might be able to say that the studies of radio versus nothing, there might be a missing study on the right here as well, that kind of thing. But yeah, that is network meta-analysis. We ran through it very quickly. If you have any questions, I'm happy to take them. Any questions? Okay, so does this mean that everything that we have explained, that we have gone through all day today has been very well understood. Someone said, can we try the trim and fill? Let's see. Let's see. I haven't tried it myself, so if we try trim and fill, that model is called net1. So let's run it. It doesn't run. Doesn't run. Yeah, doesn't run. Yeah, it doesn't run. There might be a different way, a different sort of codes that are used in network meta-analysis for trim and fill. But yeah, it's not the regular trim and fill. And sometimes, it might just not exist. Sometimes it's the case that the R hasn't developed up to that point, or it might be a case that the math, the statistics underlying network meta-analysis has not yet gone to that extent yet. I don't know. I just don't know. Yeah. Or it might just be my own ignorance of it. But yeah, thank you very much for spending your weekends with us. We will send out a survey that we hope that you will fill. It helps us to understand how we have done. Two surveys actually. One of them is a quick quiz that just looks at what you have learned in the class, and then the second one is a survey where you can be able to express your thoughts about the class, if there are things that you think we should change, if there are things that you think we should improve. This is the final session of the classes. The other component of this class is the group projects. And we know that some people have had some challenges with the groups, but we also know that some groups have been able to make a lot of progress. So we're hoping that you can all come next I think the date is the 11th of March, where the groups will just do a quick presentation of, what they have done, what their question is, what papers they have seen, and where they think they might take the paper forward to, right? I think it might be a good opportunity to see, what everybody else has been working on and how far you have come. We are very grateful to you for the time spent. We're excited about the work that you're doing in the projects. We think that some groups might be able to advance their projects to publications. I think that's very important to do. We are happy to support you as you go. So please reach out to us, and even outside of the class, we're happy to support in whatever ways that are possible. Thank you very much. If anybody has any final questions and comments, I will take them. Otherwise, we can call it a day.